So the last special transformation that we're going to look at is absolute value functions. If you know how to graph the graph inside, so you graph f of x first, what happens when we do the absolute value of it? Well, what does the absolute value do? What's the absolute value of 5? 5. What's the absolute value of 7? 7. What's the absolute value of negative 2? 2. So the absolute value, all it does is makes everything positive. So when we do a graphing thing with the absolute value, the graph of y equals absolute value of f of x will be completely above the y-axis. I mean above the x-axis. Because all of your y values will be positive. What that's going to do is whatever was negative in your original graph will just get flipped up over your x-axis. As far as transformations go, it's actually a really easy transformation to do. So here is our first example. Given f of x is 2x plus 3, can we graph the absolute value of f of x? So same thing we did with reciprocal graphs. Step 1, graph your original function. How do I graph 2x plus 3? It will have a y-intercept of 3, a slope of 2, so down 2 over 1, up 2 over 1. And it will look like that. Now, when we flip the negative part over, a key point is going to be your x-intercept. What are the coordinates of my x-intercept on that green line? Something, 0. Now, if you can see it right from the graph, great. If you can't see it from the graph, how do we find an x-intercept? Algebraically, make y equal to 0. So if I made y equal to 0, and I solved for x, I would get negative 3 over 2. Now, when we go to graph our absolute value function, that point's going to be important, because that's where your graph changes from being positive y values to negative y values. In fact, everywhere where our graph originally was positive, so for example, here at 3, the absolute value is not going to change. So this whole side here stays exactly the same as our original graph. But our graph where it was negative, and I'll highlight it here in red, the part where our original graph was negative, that's going to get flipped up over the x-axis. And this will be our new graph. Now, you could have graphed this using the skills you learned in our very first chapter. When we did, because this equation that we have here is the absolute value of 2x plus 3. And in our first chapter on transformations, we learned that one of our parent graphs was the absolute value of x. So if we were going to do transformations, working from left to right, what would the 2 do? It would times all your x values by half. And what would the 3 do? It would move it 3 to the left, but we have to remember when we have a horizontal stretch or compression with the horizontal translation, what would we have to do first? Factor. Right? Every time that you have horizontal stretches with horizontal translations, you have to factor first. So if we were doing this the same way that we learned in our very first chapter, we'd factor out that 2. That's where we'd get our plus 3 over 2. We'd multiply our x values by a half. Can you see that that would make our absolute value graph more narrow? And then move it 3 halves to the left. Can you see that that matches up perfectly with our other graph? Now, thinking back to our first method and thinking to what we did as a second method, in this case, I like the second method better. I think it's quicker. What we just learned today. It's not hard to graph the line and flip the bottom part up. Where in this part, what are you going to forget? You're going to forget that factoring out. And you're going to move it 3 to the left instead of 1.5 to the left. So for this one, we have 2 different methods. But for some other graphs, you won't have other methods because it won't be one of your parent graphs. And you'll have to graph the inside function first and then flip up whatever's below above. So here's our last example. The graph is already given to us. So, I mean, if you had to graph this and it's in its factored form, from our polynomial functions unit, you would have been able to say, I know what my 3 x-intercepts are. They're at -3, 0, and 2. And what kind of graph is this? This is an x-cubed graph. So, and it's a positive x-cubed graph, so I know that it acts like a line from left to right. So it's going to start down here, go through my x-intercepts with some loops, and end going up forever. It's a nice way to end. We get a review like we've reviewed 3 different chapters already. Now, if you want to graph the absolute value of this, we remember that the absolute value, what it does is it keeps positive values the same. So in this graph, can you see that this part would stay the same? And that part would stay the same because our y values are positive. But wherever our y values were negative, they're going to get flipped over the x-axis. So this would be our final graph. And with that, we are done.